I'm going to be talking about using word embeddings and Lucene and Solr points in order to drive concept search. So the agenda is I'll explain a little bit about what I mean by direct concept search, introduce word embedding a little bit, discuss some of the problematic nature of using word embedding vector proximity to imply synonymy, a short intro to Lucene Solr dimensional points, some Lucene modifications I had to make in order to make this work, data processing I did, a program I wrote to do query expansion search, and some conclusions. So the basic idea of what I'm calling direct concept search is to map both query and index term into a conceptual space, and then improve recall by expanding queries with these concepts. One way to represent concepts is, as in WordNet, as synonym sets. So synonymy is a sort of core to that. And it happens to be the dominant relation discoverable via proximity and word embedding. Other relations are interesting, but I'm not going to be exploring them here. Some examples that word embedding can represent: meronymy, holonomy, that's the part-whole relation; hypernymy, hyponymy, conceptually broader or narrower. And one of the standard examples is given about word embedding vectors, that you can perform vector math on them to describe analogies. So in this example, if you subtract the vector for man from king and add the vector for woman, you come quite close to the vector for queen. If you subtract woman from both sides, then you could restate that as an analogy which runs something like king is to man as queen is to woman, the relation there being has gender or something like that. So that and many other relations using vector math are representable via word embeddings. I'd be remiss if I didn't mention that a couple of years ago, a talk about something quite similar was given at Revolution. It's an excellent talk by Simon Hughes, and if you're interested, I recommend you go watch that. So word embedding, 60 years ago, something like that, maybe more, English linguist John Firth wrote, "You shall know a word by the company it keeps," which is sort of the general idea behind word embeddings, that a word derives its meaning in large part through the context in which it appears. So word embeddings are reduced dimension representations of words. Each term is represented as a vector of real numbers of varying number of dimensions. And these are producible via various methods, including training neural networks using software such as Word2Vec, which is what I used for this talk, GloVe, GenSim, Deep Learning 4J, quite a few other packages as well. Word2Vec specifically supports two algorithms, continuous bag of words, which is capable of predicting a word given the context, and continuous scriptgram, which does the reverse. The distance between two vectors can be seen as a predictor of relatedness. Next couple of slides, I talk about some problems with using distance between vectors as implying certainty about synonymy. This table below comes from the paper that I mentioned there, Leuenberg's, a minimally supervised approach for synonym extraction with word embeddings. What they did was they were attempting to use automatic methods to extract synonyms from news corpuses in English and German, and they found that precision and recall were extremely low, something like 10%. And so what they did was they manually looked at, excuse me, a subset of English words and tried to figure out what the relation actually was between the most similar and the second most similar of terms to the words that they had chosen randomly. And only, a not very large subset actually related to synonymy there. You can see that Their first category is WordNet synonyms. The next, human synonyms, which just meant that they were judged by humans as being synonymous. Spelling variants, which is probably something you want if you're doing search, but not necessarily synonymy. And you can see there's a bunch of other forms of relations that could be interesting depending upon the sort of search you're doing, but which isn't necessarily going to give you the exact same concept. So anyway, what I'm driving at here is that using similarity between word embedding vectors isn't necessarily going to perfectly align with a conceptual search. Over there on the right, I list some things they tried to do to improve the situation. And they found that if they trained multiple word embedding models with different parameters, for example, different number of dimensions, and then found agreement between models for a particular term for the most related term, that it increased the likelihood that the relation was actually synonymy and not one of these other sorts of relations. Another thing they found that helped was using part-of-speech tags and embedding those in the vocabulary for the corpus over which it was trained. This is another paper I found when I was researching for this talk, using word embeddings for automatic query expansion by Duapayan. And what they found is that using something they called incremental K-nearest neighbor, in which they would iteratively reorder a set of candidates, K, some large number, such that the ones that they retained were the ones that were most similar to other candidates, not just to the query word. And then they would prune the least similar at each one of these iterations until they went through the whole list. And that improved the likelihood of the relation actually being synonymy. Finally, another challenge with word embeddings is polysemy, which is that all senses of a surface form are treated as if they were a single concept. And I give an example here of cat, which can refer to an animal, a person, in some dialects, an equipment you manufacture. And so in a corpus that contains all of these concepts, then the vector is trained over multiple unrelated contexts, which can reduce the distinguishing power of the vector. So here's my intro to Lucene solar dimensional points, which, as I said, I'm going to be using to drive K-nearest neighbor search. They were added in Lucene 6.0 and replaced the trinumerics that previously were the way numerics were used in Lucene. Lucene 7.0 will actually completely remove tries when it's released later this week or early next week. Solar retains tries, although they've been deprecated. So points is the way numerics are done and will be done anyway, and Lucene and Solar going forward. Points can be used to drive faster range search, K-nearest neighbor search, which is what I'm going to be using it for. And they allow for storage of values that have between 1 and 8 dimensions and can be between 1 and 16 bytes in length. The underlying data structure is called a block K-dimensional tree, also called BKD trees. And they're just a binary tree with multiple values in leaf blocks. And the default in Lucene currently is 512 to 1024 in a leaf block. Over there is an image I stole from the KD tree page on Wikipedia that visualizes splitting a three-dimensional KD tree, first at the red box, splitting in half, then the green boxes, each of those two is split in half, and once more the blue boxes split. So it's a recursive split along the widest dimension until a block contains fewer than the configured values that I mentioned above in a leaf block. Next, I'll talk about some modifications I had to do to Lucene in order to be able to support more than just 8 dimensions, because word embedding vectors require significantly more than that. By default, for example, the Word2Vec implementation uses 100 dimensions. And for what it's worth, I was using Lucene 661 for these experiments that I'm going to be describing. Prior to Lucene 6, when points were first introduced, the limit for BKD, as it was previously called, values was 255 dimensions for a couple of months or something like that. But then, before the release of 6, it was reduced to 8. So the first thing I tried was just increasing that BKD writer constant max dims to 300, and that sort of seemed to work, just doing nothing else but that. But when I indexed more than a few points, I was getting exceptions about decoding negative dimensions, which seemed bad. So with some trial and error, I found that 127 dimensions without any other changes, except for the next one I'm about to mention, worked. And this other change is not exactly a change so much as it is swapping out the default codec for points format codec that increases the in-heap sort memory that's used. The default's quite a bit smaller than that. That's the maximum, 2 gigs. Finally, there is no nearest neighbor search for arbitrary points in Lucene at this point, but I was able to steal the idea from the latitude-longitude point, which has one. That's in the sandbox module in Lucene. In some ways, actually, my implementation was a simplification because latitude-longitude point calculates distance in meters between 2 points on a sphere in polar coordinates, and special dateline handling is required. Whereas for arbitrary k-dimensional values, that sort of thing isn't required. It just calculates a Euclidean distance between 2 points using the Pythagorean formula, which I give there. The square root of the sum of the squares of the difference between each dimension of a pair of vectors. So the data I used in order to do these experiments was a Wikipedia dump I had laying around from January 1st, 2016. It has about 5 million articles, 57 gig uncompressed. I converted it to plain text with Giuseppe Attardi's Wiki Extractor project, fairly new, but did a great job just cleaning up all the Wikimedia syntax and giving me just plain text demarcated by the document IDs. Then I used OpenNLP's pre-trained English model to do sentence segmentation for a couple of reasons. First of which, the Word2Vec software I was using expects sentences, 1 per line, but also because I wanted to explore identifying phrases and finding conceptual matches between individual words and phrases. I didn't want to match phrases across sentence boundaries, so that was the other reason I did sentence segmentation. Then I tokenized the data with Lucene standard tokenizer, lowercase filter, and performed significant phrase identification using a program that comes with Word2Vec called Word2Phrase, which produces bigrams and writes out a copy of the data. I had to run it twice because I wanted to go higher than just bigrams, and in so doing, it produces up to 4 grams. And the result is a vocabulary of about 4 million terms, more than half of which are phrases, and 1.7 billion words or phrases in the corpus. I then used Word2Vec to train over the corpus. I give the command line I use there. I guess the significant things is that I use the continuous bag of word algorithm with a window size of 5 and the number of dimensions I determined I could use with Lucene, which is 127, and a threshold minimum term count of 10. So I didn't include in the vocabulary terms that occurred less frequently than that. And along the bottom there is just an example line from the file that gets produced. It's just 127 floating point numbers after the term. I don't know what that was. Okay, so the next thing I did was I performed indexing, and I did that in 2 steps. It wasn't my original intent to do this. I had thought that I would be able to produce a single index that contained vectors for each term in the corpus for each document. But my first experiment created an index that just had each term, that had a document that was just a term and its vector as a point. Took so long to index that I figured it would probably take a couple, like 100 times more time for that to occur in the, indexing the entirety of Wikipedia with within a word embedding vector for each term in each document. So I didn't even attempt it. So I created a sidecar index with each document, as I say there, initially on a solid state drive, but segment merging was performing offline point sorting that used up all free space, so I had to stop it after it went up to 100 gigabytes of usage. Switched to a larger rotating disk, and indexing took about 5 hours with disk usage peaking at about 60 gigabytes. Lucene has some things that look to see whether or not it's operating over a spinning Rust disk or a solid state drive, and is more aggressive with its usage of it if it finds a solid state drive. So I assume that's why there was a difference there. And the resulting index is only 2 gigabytes long. I then just took 30 minutes to create a full Wikipedia index with a single content field, and the result was 10 gigabytes in size. Then I wrote a program to augment queries, starting with the Lucene demos search files program, and used the same analyzer that I used to prepare the data initially, but added a shingle filter to produce a superset of the phrases that were produced by the Word2Vec word-to-phrase program. Then I expanded query by looking up vectors for each analyzed term, adding those vectors together to produce one, and then doing a KNearest neighbor search with k equal 1 against this sidecar index and adding the resulting term to the final query. So this essentially takes all terms from the query and attempts to find the most related term to those terms in combination. I also did a KNearest neighbor with k equal 2 for each of the analyzed terms individually, and then added those terms to the final query. And then I queried the Wikipedia index with the expanded query. Note that this is not direct concept search, so I've done a bit of a bait and switch here. As I said, my initial intent was to have a single index that I could directly query against using word embedding vectors, but that was not to be. So next, I'm going to see if I can do a demo. I'm not sure if that's going to work, but we'll try. Is that visible? Not really. So I've already run the program a single time to sort of warm it up. I entered the query Top Gun. If any of you are familiar with the search files program that comes with the Lucene demo module, it does paging search for you. Let's see, the one query that I was trying previously, New York Jets, they have a summer camp at the State University at the campus in the city that I live. So that's why I know about them. I don't really follow sports otherwise, sorry. quite sure. Maybe I could. So this is pretty slow. It's telling us what it's doing following the setup that I described before, where it combines each of the terms that are produced by shingle filter over New York Jets. So there's New York Jets, York Jets, and Jets. When it looked up each one of those and combined those vectors, the closest vector was for Pittsburgh for some reason. Not really sure why. Maybe because it also hosts like New York City, it also hosts a football team. And then it's telling us the augmented terms, or the closest terms at distance 1 and 2, or for k equals 2 when doing KNearest neighbor search. So it shows the distance that was calculated over them. I left in place the closest one, which will be, of course, exactly the same one. When it's searching for terms, it'll find itself. And I didn't trim them from the query, which I suppose could skew it a little bit, but whatever. I also did not use the distance in order to sort or bias or boost the query in any way either, although that could be done. So this is not that great in terms of what it returns. Usually when people search Wikipedia, they search the titles, and that does quite well. But this data has the title mixed in with the rest of the content, and so I'm searching against that whole thing, and searching for the New York Jets, even though there is a page called New York Jets, isn't necessarily going to catch it. The first one there is a 2003 TV show for kids called Generation Jets, and some Jets seasons, so not bad. Anybody else have a query they would like me to try? The gentleman suggested to be or not to be. I'll give it a try. Awesome. Oh, I know what I did. I was supposed to hit enter first. I'm a stupid program user. So, restart the program. You don't have to use it. That's what you mean. Right. No stop words here, though, so. No, not engrams, shingles, which in Lucene Solar, there's a difference. Engrams are character engrams. Word engrams are called shingles, just so there's a different word to refer to them. Okay, trying again. And the closest term to all of those is the word be. That's interesting. You may notice that it's not actually producing phrasal terms for all the possible combinations, in part because it just ignores one that don't exist in the vocabulary. So apparently, the algorithm used by Word2Vec's Word2Phrase program, which is something like point-wise mutual information, doesn't think to be or ought to be a phrase. So have been, however. Wait a minute, that wasn't even one of them. So apparently there were no shingles that actually are phrasal terms in the vocabulary that was produced. That's interesting. Yes. Okay. Yeah, this is terrible. None of those look like, do these look like anything that has anything released? What was the name, Haas, again? George Washington. Okay. What? That looks like a mistake. Huh. Maryball, Washington, sure, why not? Okay, that was fun. Any other suggestions? If not, we'll switch back. Pardon? Solvamics? Ceramics, sorry. Right, so this is a dead stupid program and isn't excluding things that are distance zero, which clearly are not going to augment the query in any way. So it's found the singular version as, because I didn't include any stemming here at all. So ceramic and ceramics are related, according to Word2Vec. That's really useful. But there's, yeah, okay. Not that surprising that it's finding things with ceramic in the titles. Okay, good enough. So, I think I'm ahead of time. Conclusions, building high dimensional points indexes with Lucene is quite slow. When points were first introduced, Mike McCandless committed an optimization for one-dimensional points that sped up bulk merging, and said at the time that two-dimensional point merging could be sped up with a similar optimization, but he did not do that. And I'm hopeful if we ever add points, multi-dimensional points to Solar, which currently doesn't have it at all, that merging can be improved, merging speed can be improved. That might make it actually possible to use this stuff. Lucene Solar should have K-nearest neighbor search over K-dimensional points. So I intend to take the implementation I made and make a JIRA for it and see what people think. I highly doubt that increasing the number of dimensions beyond the current limits will be something that people will accept, at least initially, so I don't intend to ask for that, but at least support for performing K-nearest neighbor search is something we ought to be adding. Word embedding proximity isn't entirely reliable for synonymy. It does do some other forms of relatedness, but expecting that you can do concept search just with proximity, probably not a great idea. Finally, in my research, I came across a library that Facebook has put out in the last couple of months called FICE that uses GPUs to do K-nearest neighbor search on high dimension vectors, and they specifically mention word embeddings as a use case that they target. So, that's the end of my talk. If you have any questions, I'd be happy to entertain them. Yes?
Are there any plans to throw NLP into like the real solar distribution?
Yes, actually, I have done some work on that and I want to get back to it.
Right now, like I have to deal with the Stanford one. I'm pretty sure there's some licensing problems can't run into.
Right. Yes, I would like to add OpenNLP. There is an open issue, as I'm sure you're probably aware, yeah, to do that. Any other questions?
Actually, one more.
Okay, go ahead.
I took another conference or presentation, some of the semantic knowledge graph. You thought about like merging the two concepts of this into that?
So the question was about another talk that described a semantic knowledge graph and whether or not performing concept search would be merged in some way with a semantic knowledge graph. I'm not sure exactly how that would be done. There was another talk that Jake Mannix gave just before me here in this room that described some things that could be done with Word2Vec specifically, I think. I haven't seen his talk, but I'm not actually sure. Did you have something in mind particularly for?
It just seems to extract out very relevant concepts out of a body of text very efficiently. So it seems using the Word2Vec mechanism, but also using other documents in the index to see if it was an actual concept in the document that you're analyzing. So like if you had like an application for like a software engineer, it has the result for software developer would be related to this document, even though it do not have the word software developer anywhere inside of it. It's pretty interesting.
That is interesting. Yeah, I'm not aware of any current efforts anyway to do anything like that. If there aren't any other questions, thank you, and enjoy the rest of the conference.